In the next few components, we're going to derive expressions for the changes in flow conditions that occur across a normal shock wave. We'll do this by asking ourselves the question, if there was such a thing as a normal shock wave in a supersonic flow, and if we applied the laws of conservation of mass, momentum and energy, how would the properties of the gas change across this shock wave? The equations we'll derive are called the Rankine-Hugoniot equations. In this video, we'll just formulate the expressions. Let's start with a sketch. So let's put a flow with a couple of streamlines in it. So there's one streamline and there's another streamline. And let's say that in this flow there is this normal shock wave forming. What we're going to do is we're going to put a control volume around the shock wave, starting immediately upstream, which we'll call state 1, and going immediately downstream, which we'll call state 2. So the flow upstream of the shock wave is at Mach number m1. It's at pressure P1, velocity V1, temperature T1, and density ρ1. And let's say that on the downstream side of the shock wave, the Mach number is m2, and we've got P2, V2, T2, and ρ2. So the first thing we do is we need to make some assumptions. So first assumption is going to be about the thickness of the shock effectively. What we're going to say is we're going to say that A1, the area of this control volume upstream of the shock wave, is equal to A2, which is the area of this control volume immediately downstream of the shock wave. So basically, what we're saying here is that the shock wave is thin. Let's now start our conservation equation. So the first one we'll do is we'll apply the conservation of mass. So that's the continuity equation. So the conservation of mass is going to say anything that's coming into the control volume at state 1 must leave the control volume at state 2, all the mass. So we can say what's coming in is going to be, flow is going to be at density ρ1, velocity V1 and area A1, and that must equal what's exiting the control volume, density ρ2, velocity V2, area A2. Now we said we could assume that the shock waves are thin, so therefore we can cancel out A1 and A2, and that leaves us with the expression that ρ1 V1 is equal to ρ2 V2. I'm going to call that equation 1. So we've conserved mass. Let's move on to conserve momentum. Now, the form that we're going to look at for the conservation of momentum is that we're going to say any forces acting on the control volume must lead to a change in the momentum of the flow. So the only forces that are acting on our control volume are going to be the pressure force acting on the upstream surface, which is going to be in the, get rid of that, it's going to be in the downstream direction, so that force is going to be the pressure acting over the area, so P1A1. And the force acting on the downstream side of the control volume is acting in the opposite direction, so we're going to have minus P2A2, and that must equal the change in momentum. So let's look at the mass flow leaving is going to be ρ2 A2 V2, and that's going to be carrying with it velocity V2, and that's leaving. So what's coming in is mass flow ρ1 A1 V1, and that's carrying it with velocity V1. So again, we can cancel out our areas because they're all the same, and we'll look at what we've got left, which is that the P1 minus P2 is equal to ρ2 V2 squared minus rho 1 v1 squared. So that's the form of the momentum equation we're going to use. We'll call that equation 2. Let's move on to conserve energy. So I'll move up the top of the page. Conservation of energy. So we need to look at what's happening across this shock wave. So we'll note that the flow will treat as adiabatic. So adiabatic means there's no heat addition or heat removal. And we'll also say that there's no work done either on the flow or by the flow. So that's going to make our conservation of energy quite simple. We're saying that the energy of the flow coming in must equal the energy of the flow going out, because we're not doing anything to it in the meantime. So we can write that as there's going to be some initial enthalpy of the flow, H1, and it's going to have some kinetic energy. So we'll say half V1 squared. So that's our total enthalpy of the flow coming into the control volume. That must equal what's leaving. So let's say the specific enthalpy is H2, and the kinetic energy, or the specific kinetic energy, is a half V2 squared. And that must equal H naught, which is going to be the same upstream and downstream if H naught is the total enthalpy of the flow. So we'll call that equation 3. Now, the last thing we're going to do is bring in a couple more equations. We're going to assume that we have a calorically perfect gas. Calorically perfect gas. So that means, first of all, because we've got a perfect gas, it says that we can relate the pressure to the density and temperature through the gas constant. So P is equal to rho RT, which is going to be our fourth equation. And we'll say that we've got constant specific heat, so therefore we can relate the enthalpy, static enthalpy, to the static temperature, so through the ratio of specific heat, or through the specific heat at constant pressure, I should say. So that says that H is equal to CPT, so that's our fifth equation. The last equation we're going to use is we're going to relate the speed of sound. So A is our speed of sound, so A squared is gamma P over rho, so we can relate the speed of sound to the pressure and the density through the ratio of specific heats. And that'll be our equation 6. I'm going to spend the next video combining these 6 equations to derive expressions for how the pressure, temperature and density change across the shock wave. There's quite a bit of manipulation of these equations to get to the answer. I suggest you get a piece of paper and work through with me as we go, pausing the video as we progress and perhaps doing a few checks as we go. You could jump straight to the next video, but then you'd miss out on all the fun.